Educational Model of Control System. SIS 5100, Modern Control Engineering, Winter 2007. Educational Model of Control System. For robot arm. Team members, Irina Karasik, Sylvain Ganter, Olivier Poulter, Jiangjia Kong, T.A. Wei Yang. Professor, Riyad Habash. April 4, 2007. References. 1. Kok Keong Tan and Han Liang Go, Development of a Mobile Spreadsheet-Based Bot Control Simulation System, IEEE Transaction on Education, pages 199 to 207, May 2006. 2. Guang Zhang and Junji Furashu, Control of Robot Arms Using Joint Torque Sensors, IEEE Control Systems, pp. 48-55, 1998. 3. Gloria Su, Daesung Yoon, Young-il Park, Ki-dong Lee, Suk-gyu Lee, Design of a Pole Placement Controller for Reducing Oscillation and Settling Time in a 2-Inertia Motor System, ICANN'01. The 27th Annual Conference of the IEEE Industrial Electronics Society, pp. 615-620, 2001. 4. Estico Rianto, Antonio Moran, and Minoru Hayes, Experimental Positioning Control of Flexible Arm Using 2 Degrees of Freedom Controller, P127. 5. Miomir K. Vukobratovic, Alexander D. Rodek, Control of Manipulation Robots Interacting with Dynamic Environment, Implementation and Experiments, IEEE Transactions on Industrial Electronics, Volume 42, Number 4, August 1995. 6. Textbook, Modern Control Theory. References. 1. Development of a Mobile Spreadsheet-Based Bot Control Simulation System. To control the temperature of thermal chamber. Mobile PED Tuning Preparatory Exercise. Mobile Spreadsheet Simulator. References. 2. Control of robot arms using joint torque sensors. 2. Inertia System Modeling. With joint torque feedback. Dealt with pole assignment. And effect of disturbance. Half bandwidth of resonance frequency. PD controller. Identical damping coefficients. 1 equals 2. A wider bandwidth and better disturbance. Rejection over conventional PD control. References. 3. Design of a pole placement controller for reducing oscillation and settling time in a 2-inertia motor system. Identical real part settling time. Comparison among 3 controller. IP, IPD, state feedback control. Conventionality. And weightedity. Full state feedback control. Is the best. In terms of oscillation. And settling time. References. 4. Experimental Positioning Control of Flexible Arm Using 2 Degrees of Freedom Controller. 2 methods. 2, is better. 1. Feedback control, frequency domain. Based on model matching. Method using the inverse dynamics of the arm system. 2. Feed-forward control, time domain. Using the inverse dynamics of the non-minimum phase system of the arm. References. 5. Control of manipulation robots interacting with dynamic environment, implementation and experiments. Our goals to design a control system for robot arm. To practice the control theories acquired in class. To provide an educational model of control theories with robot arm model. To help the students understand the control system theory and increase their interest in the subject matter. Team and role start topic selection role assignment references search. Irina Karasik, Model Analysis. Sylvain Ganter, Controller Design. Olivier Poulter, Simulink. Jiangjia Kong, Controller Design. Leader. Weekly, Meeting. Plant modeling. Controllers design. MATLAB simulation. Educational model. End. Steps: Step 3 Step 1 Actuator plus process, robot arm. Step 2 Controller GUI. Input. Reference. Output. Arm dynamics. Controller. GUI. Controller gain adjust. Step 3. Step 1 Analysis of system characteristic, from the dynamics of robot arm. Step 2 Controller design, P, Pi, PD, PID, phase lead or lag compensator. Step 3 Simulation, MATLAB, and user interface design, Simulink. Step 4 Evaluation of the performance of the controlled system, dynamic model of robot arm. 250. SS plus 2S plus 40S plus 45. G, S, equals. Characteristics of plant model. State space model. -87 -1970 -3600 1. I equals 1000, B equals 0. 01000, 00100, C equals 000 D equals 0. Characteristics of plant model. Location of poles and zeros. Characteristics of plant model. Steady state error, type. Step input. S equals 0. Ramp input, with unit ramp input. KV equals lim SGs equals 0.0694. S equals A/KV equals 14.4. Parabolic input. S equals. Characteristics of plant model. Controllability and observability. Det, PC, equals 3.9109. Process is controllable. Det, PO, equals 1. Process is observable. Characteristics of plant model. Time response and frequency response. Ts equals. P.O equals. Phase margin equals 87.8 degrees. Design criteria. Settling time, T is 1.2 seconds. Maximum overshoot. P.O 20%. Phase margin. PM 45 degrees. Controller design unity feedback control. Ts equals 80 seconds. P.O equals 0%. PM equals -180 degrees. Controller design P control. Settling time is several times greater than the desired value. Ts equals 4.26 seconds. P.O equals 20%. PM equals 79.7 degrees. Controller design Pi control. Settling time is still too large. Ts equals 4.25 seconds. P.O equals 20%. PM equals 77.3 degrees. Controller design PD control. Settling time is better, but still does not meet our criteria. Ts equals 1.43 seconds. P.O equals 20%. PM equals 96.7 degrees. Controller design PID control. Settling time is better, but still does not meet our criteria. Ts equals 1.75 seconds. P.O equals 20%. PM equals 69.1 degrees. Controller design phase lead compensator. Ts equals 84 seconds. P.O equals 20%. PM equals 45 degrees. Meets our design criteria. Loop transfer function. Controller design. Phase lead compensator, continued. Open loop. Loop transfer function. Closed loop, educational GUI design. Open loop response. Closed loop response input selection controller selection output scope. Root-locus. Drawing. Scope. Selection. Controllability. And observability. Check. Comparison. Between controllers. Pole 0. And others. Bode. Plot, closed loop response. System analysis, pole 0 map, root-locus, Bode plot. Controller selection and parameter change. Comparison between two controllers. System output analysis. Conclusion. It is not possible to meet the design criteria with P, Pi, PD, and PID controller of this ARM model. Controller gain change effects on both. Time, overshoot. The best controller for this model is phase lead compensator. Student can learn the control theory easily. Parameter change see the effect. Two different controllers compare the effect.